Hi everyone. Welcome to the Topos Institute Colloquium. Today we are pleased and honored to have Mario Román from Oxford, who will be speaking to us about partial Markov categories. So Mario, whenever you're ready.
Thank you so much, Howie. So I'm going to be telling you a story about probability theory and category theory and how to get a good language for probability theory. So first, let me say that this is all written up in two papers. The first with Elena de Laboren, and the second, more recent one, is with Bar Jacobs. Both are on the archive in case you want to have a look. We will mostly follow the first one, prudential decision theory and partial Markov categories, but I will also take some examples from the second one. Right, so let me first give you the motivation. The idea is that even if we may think that we know how to solve problems in probability theory, the fact is that probability theory is generally difficult. You could think that probability theory is solved, or at least that in the discrete finite case it is solved. We know how to compute, how to solve every problem. But then it can happen that you go around, like Barda did in a paper last year, you go around asking your colleagues in the medical field or in AI how to update after taking some tests to a disease. You give them the specificity and the sensitivity and so on. And then you get different answers depending on how you ask. So there was a paper by Bart last year about this. This is a question that is important, that seems simple, because it's something that is basic discrete probability theory, that is important because it could have policy implications, but then not everyone agrees on what is the correct answer, or knows, even if they could agree on the answer, they don't know how to explain the reasoning. If you give me this question, perhaps I start writing numbers and computing things, and I don't really know how to explain to you what I'm doing. So there are multiple problems here. The first one is that when we solve a probabilistic problem, we assume many things, and we do not even mention all of them. So many things remain implicit. If we had a good formal language, at least these assumptions would have to be explicit. And to a certain extent, that's what happens in probabilistic programming or in some combinatorics and probabilistic papers. But we could further and say, well, there is another problem, that is that perhaps instead of discussing analytic probability, there could be a bunch of simple axioms, simple postulates that give a synthetic theory of probability. So when I say synthetic here, I mean in the opposed to analytic. You know, like in analytic geometry, you use Cartesian coordinates and you solve equations to know if two lines meet. While in synthetic geometry, you use Euclid's postulates, and then you try to develop a theory of how geometry behaves. So the first develops a single model, the second gives a theory. We could think that there is something like that for probability theory, and that is what we are going to try to get. Right, so to give an example of the kind of problems that we are going to face, let me give you the paradigmatic example of probabilistic decision theory. This is the Monty Hall problem. So the Monty Hall problem is a famous problem in probabilistic decision theory because it is very easy to get it wrong and to interpret it in subtly different ways that give different answers. So it starts with a TV show. There is some prize behind exactly one of three closed doors. And there is a contestant that can pick to open one of the doors. And if they find the prize, they can keep it. So now I will be telling you about the problem, and then at the same time, I will be keeping the formal account of the problem on the other side. I'm not going to explain the details, not the computations, and then during the rest of the talk, I can go on how everything that I'm going to use now works. So we start with a prize that is distributed uniformly behind three doors, the left, middle, and right doors. The contestant is going to pick one of the doors, say they pick the middle door. And now we have that the prize could be on the left door, and the contestant has picked the middle door. With 1/3 probability, the prize could be on the middle door, and the contestant has picked the middle door, and so on. If you see the choice of the middle door doesn't have any effect, it's independent on where the prize is. Now, if the show would end here, the probability of getting the prize would be 1/3, but because this is TV and we need to make this spectacular, now the conductor of the DB program appears and says, well, I'm going to open one of the 3 doors. And I'm going to do that in such a way that I will not open the door revealing the price. I will not open the door that you picked. Right, so we compute how that works on the right. And that would be assuming that the conductor takes a uniform distribution if they can open more than 1 door. So in the case that the contestant pick the middle door and the price is on the middle door, they can open either the right or left doors with equal probability. They now open the right door, and we need to discard all the possible worlds where their left door would have been picked. And then we are left with any distribution, and the conductor asks, well, the contestant can now change doors. I allow you to change doors if you want. Now the question is, should the contestant change doors? If you follow the calculations, if you have been following the calculations, you now obtain that the left door has a 2 in 3 probability of having the price, while the middle door has just 1 in 3. This is traditionally controversial, with people claiming that perhaps the probability is 1 in 2 for both doors. But what we are going to do today is to have some formal object, the string diagram that I am depicting on the right, that leads to the calculations that we have below. So if you agree on the string diagrams and the contents of each one of the nodes, then you need to agree on the computation. So if we agree on the modeling of the problem, we are going to agree on the solution. So because this is now a formal mathematical object, there will be also a translation to code. We can translate the string diagram to code. We will define each one of the functions that are implied, and then we can leave the computer compute the correct solution. So what we are contributing here is the formal language that does this, both with string diagrams and then the translation to code. For this talk, I'm going to be talking about the string diagrams. The translation to code then is relatively easy. But in the second paper that I linked at the beginning, you can see in the second. Right. So let me try to build the structure that we need for this in multiple stages, in multiple levels. So the first one is that of copy discard categories. We are going to start seeing a very basic structure where we can control the information flow. Then we are going to see partial Markov categories. And then we're going to add extra algebraic structure that is going to allow us to talk about certain theorems that we could not talk about in partial Markov categories. So we are going to see this discrete partial Markov categories. And at the end, we can see some examples in continuous probability, and if we have time, in decision theory. So let me go quickly through copy discard categories. The idea here is we are going to use string diagrams for a symmetric monoidal category with a comonoid structure, which means that we are going to go have a copy, a discard, and this is going to be commutative, unital, and associative. So then we need to give some semantics to the nodes we are going to use. These are going to be sub-distributions. So as a channel between X and Y in these sub-distributions is going to be some collection of numbers indexed by X and Y, and such that every time we add over Y, that needs to add at most 1. So they are going to be all positive real numbers, and they add always less or equal than 1 when we sum over Y, over the output. Then we are going to have a copy node, and the thing that is doing is checking equality between from the input to the 2 outputs, and a discard node that always returns 1, the constant distribution 1. If we have these 2 channels, 2 distributions, we can tensor them, assuming they are independent. So this is to say, what is the probability of Y1 giving X1 and the probability of Y2 giving X2? That's the product of the 2 probabilities because we assume them to be independent. And then what is the composition? So if we want to know what is the probability of Z given Y, and then the probability, of Z given X, then we need to ask what is the probability of Z given Y for any Y, and the probability of Y given X. And then we add over all the Ys, and that's the probability of the composition. So this gives semantics to the copy discard categories for these distributions. But this is not the only semantics we could give. A different copy discard category is that of standard Borel spaces. And then we have Markov kernels between them. Here we are going to have sub-distributed Markov kernels. So we ask that they all integrate to less or equal than 1. The copy could be the delta distribution, the discard is still 1, and then we need to use integrals on the composition. But the idea is that we could give different semantics. And we are going to pick mostly today the discrete semantics and only at the end see the continuous semantics, just because it's easier to follow. So we can already talk about some aspects of probability theory. We can say when a function is total, when a stochastic channel is total. And we can say so not only by the semantic side, by saying that distribution is total if it has real distribution with measure one, but we can also encode that in the syntax. So that would be encoding it not only analytically, but also synthetically. In the syntax, we say that a channel is total if we can discard it, and that is equal to just discarding the input. Now, let us read the string diagrams with the semantics we were given before. The string diagrams here are saying that we add over y, because this would be the composition of f with a discard. So we add over y, and that needs to be equal to 1. That is the value of the discard. So we are saying that a distribution is total if it adds up to 1 always. When is a distribution deterministic? So a distribution is deterministic when it satisfies the formula here. That is to say that the probability of y1 given x and y2 given x multiplied needs to be equal to the probability of y given x, and then we multiply by this Dirac delta that checks that all the y's are equal. So this seems a complicated formula, but the idea is that if they are equal, then we are saying that the probability squared of getting y given x is equal to the probability of y given x. That is another way of saying that the probability is either 1 or 0. So all the probability mass is concentrated on one point, and now the channel, the stochastic channel, is deterministic. So these are two notions that you could discuss about stochastic channels, but now we have a way of discussing them using just syntax. We can say what it means to be total and deterministic, and it's these two equations of string diagrams on the left. We can do some more some more probability theory, even with very little category theory. We have only introduced a comonoid. The idea is that we can do also marginals and pass the inputs. So the first operation that I have here is marginals. If we have a channel with two outputs, so we can compute the probability of y and z given x. We can add up on the side of the y all the probabilities, depending on all the possible y's, sorry. And then it will be the marginal of the channel h on z. So we can do marginal distributions, and we can also copy the input and pass it to the next morphism. So copying the input, the idea would be I send some input to some morphism, but I also keep it to use it later. And then I'm just saying that the output x prime needs to be equal to the inputs, and then that we have some channel that still computes the probability of y given x. So these two operations are important and are related because they form a section retraction pair. So if I take the input copy of a morphism and then I take the marginal, that gives me back the original morphism. And we can use that to compute something that is called conditional composition. So if you see, the idea here has been before to have some idea of what marginal distributions are, of how to pass an input in the semantic of distributions. Now we abstract it and it becomes some string diagrams. And now with these string diagrams, we can define new operations that are going to be important later. So the idea here is to define conditional composition, which is composition conjugated by marginals. So this is a very difficult way of saying we are going to keep the input, and we are going to also pass it to the next morphisms. And then we are going to delete it once used. So conditional composition is to compute the input copy of f, compose it with the input copy of g, and then project and take the first marginal. This is a composition that is also associative and unital. It doesn't form a category because you need to be careful with the types, but it's just a composition of the usual category conjugated by marginals. And this idea of composition, this conditional composition, is interesting, and we're going to call it like that because it makes the second morphism be conditioned also on the input to the first morphism. So we say that a morphism has conditionals, and now we are recovering the notion of conditionals if it can be factored through the conditional composition of the marginal and some other morphism. So we say that f has conditionals. F is now a channel with two outputs. If I can forget about one of the outputs, compute the marginal, and then with conditional composition, so passing the input on the output to another morphism, I can recover my original x. F, sorry. So if we read the string diagrams to formulas again, what we are doing here is saying that the probability of y and z given x is going to be the sum, so this sum here over z of the probability of y and z given x multiplied by some morphism, some quantity that is going to be given by a different distribution. So here I should have put the parentheses so that you know that you can divide this and you compute now what is this conditional. So the conditional is going to be, well, if I want to compute the probability of z given x and y, I need to compute the probability of y and z given x and then divide that, renormalize that by the marginal. So this works always unless this marginal is 0. So the problem we have is that conditionals are going to exist, but if you see already in the semantics, we find a problem. That is that you could pick the value of C if this sum is 0. When the sum is not 0, then the value is determined. When the sum is 0, then you could pick whichever value for C and it will work. So what we cannot say is that conditionals are going to be unique. And if you were to ask in the syntax that conditionals are unique, you would find that you can prove equality between any two morphisms. This is on a paper by Fritz, where he introduces all the story of Markov categories. But the thing you can say is, well, conditionals are not going to be unique, but I can consider what it means to be almost surely equal, because they are going to be unique on the domain of this f, on the places where this f is not 0. On the inputs and outputs where this f doesn't say that it's impossible to get that y, right? So if in the sum before this is 0, I'm saying that it's impossible to get y. And we should have never arrived to that point where we ask the conditional, what is the set depending on a y that is impossible. So except on that case, conditionals are still unique. So we can ask now in the syntax that two things are almost surely equal if with respect to a morphism, if precomposing conditionally with that morphism gives the same result. Conditionals of f are going to be f almost surely unique, even if they are not unique, and we are not going to ask for that in the syntax. So we arrive to the definition of Markov categories. The idea is that we have a copy discard category where every morphism is going to be total, so that we ensure that they are distributions, and has conditional. So it can be factored through the marginal in this way that we are describing. So this is the definition of Markov categories. And here there are two assumptions. One, I am trying to justify that is important for probability theory, which is that of conditionals. The other one seems to be less important, and is that the distributions are total, that they add up to 1. So this is what we are going to drop in this second part of the talk, where we go to partial Markov categories. So partial Markov categories are the same as Markov categories, but now we don't ask for all the morphisms to be total. So a partial Markov category is a copy discard category where every morphism has conditionals. And I don't ask for uniqueness of conditionals, and I don't ask for totality. The idea here is that before we were asking the distributions to add at most 1. And if we only ask them to add at most 1, and we don't ask them to be total, to add up to 1, then the thing we have is not a Markov category, it's only a partial Markov category. So we are going to see in partial Markov category the idea of domains, normalizations, and Bayesian inversions. These are things that we could not describe in a Markov category precisely because of this restriction of totality, but that are still important for probability theory. So let me give you normalizations and Bayesian inversions and domains so that we can discuss later if we have time. But I think the most important thing here is Bayesian inversions. That is something that we could not yet do in the Markov category inside the syntax. So let me first give normalizations. So the normalization of a morphism is going to be a morphism, the n of f, that satisfies the following equation on string diagrams. Now I need to explain why I'm choosing this equation of string diagrams to define normalization. If you read the string diagrams, what is happening here is that we multiply the normalization by the marginal of f on all its outputs. And if you pass that dividing, the thing you get is f normalized, right? This would be the last formula we have here. So if you see, this recovers the notion of normalization in distributions. Of course, this as we were doing with conditionals, this doesn't always work. This requires that sum to be non-zero. So normalization is not going to be unique, but again, we can do the same thing that we were doing before with conditionals. It's going to be f discard almost surely unique. Now, normalization was something that we could not define before because we were assuming that all morphisms were total. So this f here would need to disappear. Now we can define normalizations. We can show that even if they are not unique, they're still almost surely unique. So except on the cases where some impossibility happens, normalizations are uniquely defined. Right, so this is a normalization of a morphism. Some authors draw the normalization because it's an operator of morphisms with boxes. I learned this from Jacobs, but I'm sure that this is something common. So the idea here is that we are going to draw with a green box the normalization and just follow the same equation that we had before. So the normalization of f is some morphism that I can put to the side, discard f, and it still does the same role as f does. But now we have a synthetic definition of normalization that doesn't rely on any particular semantics. So can we prove things about normalization in this description? So we can prove some things that are true of normalization and realize that some things are not true. The first thing that you would like to try to prove is, well, perhaps this is a functor box. Perhaps normalization is functorial. And this fails. Normalization is not functorial. It's not the case that the normalization of S composed with G is equal to the normalization of F composed with the normalization of G. You can see that failing already in subdistributions. What is true, however, is that if you want to compose the normalization of a composition, you can normalize the first part, then compose, and then renormalize. You can renormal, if you are doing a sequential composition of distributions, you can renormalize at any point and then continue your computation. And if you only care about the normalization, this is fine. So I wanted to do this proposition just as an example of how we reason with normalization in partial Markov categories. So the idea is that we need to prove that the normalization of f composed with G is a normalization for f composed with G. So then we need to prove that the thing on the left equals the thing on the right. So the first step is to use the definition of the normalization of f. So we put the normalization of f here. The second step uses associativity of the comonoid, so just rerouting the flow of information. The third step uses normalization of the normalization of f composed with G. And then again, by definition of normalization now of f, we get to the final morphism. So this is something that we deduced from the axioms, and the axioms were very little. We just assume the existence of a comonoid and then the definition of normalization that we are using. We can also show that normalization is idempotent, right? That the normalization of the normalization is almost surely the normalization again. So how we do that? Well, we assume we have the normalization of the normalization. In the first step, we include the normalization of f. Then again, we use associativity to route the flow of information. And then we say that, well, the normalization of f can be substituted by the normalization of f. And again, by definition of normalization, we get back to f. So it's a reasoning that is a bit complicated. It would be easier to check it on a single semantic. So now we are doing everything syntactically, right? And the proof works for all the models that we may have of copy discard categories with normalizations. We can do something a bit more difficult, that is Bayesian inversions, or more general. This is something that you can do also in Markov categories. The idea here is that if you have some prior and you are seeing it through a channel, so you have some X and some Y that you get through a channel F, there is a way of inverting that channel F so that if you would be given the other side of the distribution, you could compute the first side. So this is a particular case of conditionals. And I think I'm not going to enter on how you deduce this from conditionals. But the idea is that there is always, if you assume the existence of conditionals in partial Markov categories, there is always a morphism that satisfies this equation. If you write the formulas down in the semantics, in distributions, you have that the prior multiplied by the channel needs to be equal to this sum. When you divide by the sum, and again, here parentheses are missing, I don't know why, sorry. When you divide by the sum, then you are getting the value of this conditional distribution, this Bayesian inversion, needs to be, well, if I want to compute the probability of X given Y, that is going to be the probability of y given x multiplied by the prior I have on x, and then the probability of y in general, so adding up over all the possible x's. So this exists every time we have conditionals, and we can use this well, first we can prove that again, it's a particular case of conditionals, it's going to be almost surely unique. You could prove that it is PF, so P composed with F, almost surely unique, that it exists in every Markov category, and this would be a lemma that would allow you to prove, this would be a lemma that would allow you to prove the general form of Bayes' theorem. So if you see, we have encoded here Bayes' theorem, and now the plan is, well, even if we can do this in partial Markov categories, what we cannot do is to express this morphism that we have here, this conditional, without doing something external, without asking for a solution to a certain equation. We would like to be able to write something that says, here I'm going to use this conditional. I want to be able to write morphisms without having to write this Bayesian inversion of f given p, right? For that, we need extra algebraic structure, and that extra algebraic structure is given by partial Markov categories. So until here, I was telling you about features of discrete partial Markov categories. Until here, I was giving you features of partial Markov categories. Now we are going to introduce a bit of extra structure and then go back to Bayesian inversions and recover a way of doing these Bayesian inversions with the syntax of discrete partial Markov categories. Right, so let me now introduce these discrete partial Markov categories. Until here, I have told you that partial Markov categories are categories that are copy-discard categories that have conditionals, and I'm only asking for the existence of conditionals. Now we are going to ask for something a bit stronger. We are going to ask that they are copy-discard categories and that they have a morphism that takes two inputs and gives one output, that is a compare morphism. So the compare morphism is meant to represent some morphism that checks if two inputs are equal. If they are, it lets any of the two pass. If not, then it makes the whole morphism fail. It should give us an error. It should say something here has happened that was impossible or that you were not expecting. So I'm going to remove from the probability mass all the things that do not satisfy this constraint of these two things being equal. So what are the actions that such a compare should satisfy? So first, if we copy some inputs and then we compare it with itself, with its copy, that should be the same as doing nothing. It's going to be still associative, because if we are comparing three things, it doesn't matter the order. It's going to be commutative, because if we are comparing two things, it doesn't matter if we put the first or the second first. And then it's going to satisfy the Frobenius law. So before I go into the Frobenius law, I want to note that it is not unital. There is a problem if we were to ask for unitarity here. The fact is that in subdistributions, already in distributions, you would not have a unit for this compare, because that would be a uniform distribution. So the unit for this compare would be a uniform distribution. But we are assuming that in discrete probability, at least, we are assuming that we are not going to be able to give a uniform distribution in any space, because we are going to have infinite spaces where the uniform probability distribution should have a value close to zero, right? Every point would have measure zero. So this is a problem in continuous cases, and this is why, in part, why we call these discrete partial Markov categories. So finally, the Frobenius equation, that is the last one, says that if we have two inputs, and we want to compare them and copy them, so the middle part of the equation, we could pick the first one, copy it, and then compare with the second and only give the second one, because they need to be equal. If they are equal, then they are going to be the same. If they are not equal, then any of the comparisons is going to fail and it's going to give an error. So in any of the two cases, the equation holds. Okay, I'm giving you a justification for the actions that we are assuming now. I could give you also the interpretation of these actions in the case of subdistributions. So in subdistributions, the compare is the function that takes two inputs and an output and gives one exactly if the two inputs and the output are all equal. This is not a total function. So this is something that we could not do in Markov categories, but we can do in partial Markov categories. Because if we were to add on the output all the values, that doesn't necessarily add up to 1. It could be that the two inputs are different and then it adds up to 0. It's impossible to make them equal. We can check that this satisfies still the Frobenius axioms. So if we are comparing for equality and then adding and copying, it doesn't matter in the order in which we do it. I'm not going to go into the details here. But the idea is that we have a discrete partial Markov category that is the category of subdistributions. So now we go back to our conditionals. I promised you before that once we have this extra piece of syntax, we could be able to do this story of Bayesian inversions inside we could represent the morphism without having to write the Bayesian inversion of the morphism. We have to have, without writing, for instance, in this slide, G condition to F inverted over the distribution F. So Bayes' theorem says that if we observe Y through a channel XY, and we know that this comes from a prior that is of type X, that we call P, once we make this observation, we should update our prior up to scalar to the Bayesian inversion evaluated on the observation. So this is a very long way of saying what the string diagrams are saying. So here on the left, we say that we have some prior given by F. We are going to copy that prior, and through a channel G, we are going to observe Y. So we compare the output of G with Y. On the other side, we are saying that this is equal up to this scalar here, or the part of the diagram that is floating apart. Up to this scalar, this is equal to evaluating Y on the Bayesian inversion on G on F. Here, the important thing is that on the left-hand side, we can write this without having to assume a solution to this equation that we were assuming before. Again, if we compute the equation and the solution to it, we are going to get the Bayesian inversion. But now we are just writing it without having to write the G dagger F in the string diagrams. Again, this works unless 0, so you need to be careful with that. But this is what I have explained before about the existence of Bayesian inversions and conditionals. I'm not going to repeat. Another question would be how this captures the usual Bayesian Bayes theorem. The idea is that the usual Bayes theorem says, well, the probability of X given Y is going to be the probability of Y given X times the probability of X divided by the probability of Y. If you see the last formula that we have the probability of Y given X on the G, that's given by the channel G, the probability of F, that is given by the prior F, and then the probability of Y is going to be, we are going to recover it by adding over all the possible X's. So the idea here is that we are naming the channels. We don't call every probability channel P, but apart from that, it's going to be the usual Bayes theorem. So can we prove that without going to distributions and checking that it works? This is what we are going to do now. We are going to prove that from the principles that we assume from the axioms of discrete partial Markov categories. So the proof goes like this. First, we start by doing Bayesian inversion. This is the point where Bayesian inversions start. But then we can continue because now we can apply the Frobenius axiom. And with the Frobenius axiom, we can change the way we compare. And now on the last step, we need to use the fact that the Y is a deterministic map. It represents some point. This is a deterministic observation and not just the observation of a distribution. When that's the case, the Y gets copied, right? That was our definition of deterministic. And then we get the final result on the right. So up to scalar, we are just evaluating Y on the Bayesian inversion. Right. So this is the Bayes theorem and the proof. We needed, in order to arrive here, we need discrete partial Markov categories. So the question is, well, if you are doing this only with discrete partial Markov categories, perhaps there is some problem when we go to continuous examples. And in some sense, there will be a problem in continuous examples. They are not usually examples of discrete partial Markov categories. And in some other sense, it won't matter too much because we are going to still be able to compute exact observations. So let me do this quickly with an example. First, let me show what is the problem. In continuous probability, categories may have comparators, so they could seem that they are discrete partial Markov categories. The problem is that they are not useful. So imagine I define a comparator as a measurable functions for standard Borel spaces that is going to check if two things are equal and then return 1 and then return 0 otherwise. So this is a measurable function. You can check that is fine, at least for standard Borel spaces. But we have a problem because the set containing just a single element, the singleton set, on any element here is going to have usually measure 0. It is impossible to get exactly a particular real number, for instance. So if we compare with a particular real number, the probability that we are going to obtain is just 0. It doesn't matter what we write after that point because we observed some impossibility. We observed that something had measure 0. This is bad because that could mean that we cannot do observations in continuous examples. And we need to have some way of solving this. So categories such as standard Borel spaces have comparators. The problem is we don't want to use the comparators that come with the category. So is there another way of keep the exact observations? This is what we are going to do next. So the idea is that even if we cannot do comparators, if you give me a Markov category, so and now this one is to be total, Markov category with conditionals, we can construct a partial Markov category, a new one that we call exact C, or a C Markov category. And this new category will add syntactically one morphism that gives an observation of Y for every deterministic Y. So in some sense, we are not adding comparators. We are not asking for the existence of comparators, but we are asking for the existence of these Ys that observe this particular element. So we add something like this generator here for every deterministic Y. And this is quotiented by one equation that behaves in the same way that observations behave. So if I have some inputs, I copy it, and I observe Y, well, that's the same as outputting Y directly, because I know that the value of that Y is going to be Y, and then moving the observation backwards. So it would affect the rest of the morphisms that came before. So we add syntactically these Ys now as observations, and we quotient by this equation that we have here. That gives us a category that is not a Markov category, even if the category we start with is a Markov category, but it's a partial Markov category. And now we can use this to do continuous probability theory. So I'm going to give you a tiny problem of continuous probability theory that is not very realistic, but it's very easy to compute, so we can go with that. We are going to assume a normal distribution. The standard deviation of the normal distribution is going to be fixed, is 1. And it has some mean that is going to be sampled uniformly from the interval 0, 1. But we don't know what is the mean of this normal distribution. Now we have this normal distribution, we don't know the mean, and we take a sample from it, and we see 2.1 out of this normal distribution. Now the question is, what is the mean? What is our posterior on what the mean is? This is the typical question probability theory that is a nice exercise that is sometimes difficult to get right. If you start doing calculations without thinking too much, you would get it wrong, or you could get confused, or you could not be able to explain what your computations are. Let's try to do that from a principal point of view. So we have a uniform distribution in 0, 1. This is the node we have at the beginning. We copy that value, and through a channel that takes a mean, computes the normal distribution on that mean, we have sampled 2.1. What we are going to do now is to invert the normal with a Bayesian inversion. And now that we have inverted the normal, we see the observation is hanging from a copy node. We can employ the axiom that we ask for observations, that they split these copy nodes. And that should be the same as computing the Bayesian inversion of the normal in 2.1. So we go back, because this was a Markov category, we know how to compute Bayesian inversions. So this is the computation I have here done, and we could do that numerically. So that's the thing I do on the graphics on the right? We do the integration of the uniform multiplied by the normal, and we will get a posterior like the one I draw there. So the idea is, if we have a normal distribution with standard distribution 1, the mean is sampled uniformly from an interval 0, 1. So that's our prior. And we see out of this normal at 2.1, then it is more likely that our mean was closer to 1 than it is that it was closer to 0. And we update on a posterior that looks like the thing there on the angle, right? And we can compute that numerically now. So for a different example, imagine we sample 0.3. We can repeat the same computation. And now the posterior looks like the mean of the normal distribution is more likely to be closer to 0.3, 0.2, 0.4 than it is to be close to 1. Right? And these are computations that now we can write in the language of the string diagrams as well. So the idea here goes to this construction of exact observations. You are going to find in the work of Statham and Stein a similar construction that is that of exact observations, but the idea is going to be the same. The only thing we're doing here is putting this on the framework of partial Markov categories. And then we can use them for continuous probability, even in the cases where we don't have, where we don't necessarily have comparators, or the comparators we want to use are not good enough. So this is how we do examples of continuous probability theory in partial Markov categories. And I think if I have still a bit more time, I could end here. But if I have a bit more time, I would like to.
You have more time. Feel free to continue.
Yeah, thank you. Thank you. Yeah, I was a bit more fast. If there are any questions or something that you want to stop me on anything, please. But then I'm going to give you, as this was the bonus slide as bonus track. Let me give you Newcomb's problem. Trying to do this now with partial Markov categories. I'm trying to argue with this last example that you can use partial Markov categories for decision theory in general, and that many problems that are controversial or are difficult to solve become easier once you write them on a formal language that forces you to make explicit all the assumptions that you're taking when you solve a problem. So the idea is, in Newcomb's problem, the idea is that you have the following characters. You are going to have an agent that needs to pick a decision. We have a being that is very accurate and can predict supernatural things. So it's going to be able to predict the actions of the agent. And we have two boxes. So the being is going to think the following. So later the agent is going to pick either the two boxes or just a single box. I can fill boxes, or I could fill just one. And I want to punish greedy agents. So what I'm going to do is, if I predict that the agent takes a single box, then I will fill both boxes. So let's say that on one I put a little, and on the other one I put a lot. And then the agent would like to take that lot. But they need to take a single box. If the agent is the kind of agent that takes two boxes, and because I'm this supernatural being that knows how to predict the actions of the agent, I will not fill both boxes, right? This is punishing greedy agents. So when you are faced to this problem, now the predictor closes the boxes and leaves. They cannot affect the scene of the problem anymore. When you are faced with this problem, you can give two different arguments. You can say, well, I should pick. Now I'm here, the predictor already left. I could pick two boxes because getting a bit more money is always better. So no matter what I do, I cannot change whatever is in the boxes. I should pick both. Or I could pick a single box. The idea being, well, I want to be the kind of agent that picks a single box so that the predictor, which is very accurate, knows what's happening, is going to be the one that rewards me and puts more money in the boxes. So now here, there is different schools of decision theory that would answer differently this question. This is a subject of some debate, right? What should you do in a situation like this? The idea in all of these cases is to always find the argument that maximizes some expected value function, but then you need to interpret what that expected value function is. So instead of that, what you can do is to use this formal language that we have been developing of partial Markov categories and write the problem in terms of observations and channels. So this is what I do in the scene diagram here. You would put that you have an agent that may pick two boxes or one box, that you have a predictor that is going to put money or not. You know that the predictor is accurate, so you are going to observe that. And this is the comparator node that you have on the right. And then depending on the actions of the agent and the predictor, you are going to get some outcome that is the utility that the agent is extracting from this problem. The idea here is that all these problems are complicated. People is going to argue about what is the correct solution. But if in some sense we can set all the assumptions, then this dispute of what is the correct solution can be reduced to a good mathematical calculation, right? Once if we all agree on the same premises, at least we're going to arrive to the same conclusion. So the thing we have been showing is that we can have a formal syntax and actions for stochastic processes and for Bayesian inference, that we can use them now for doing systematic decision theory. So problems like this you will find in the two papers I linked at the beginning, and we try to solve them in a systematic way. And then as a result or part of the idea, you get a good theory of synthetic probability, an abstract theory with a bunch of postulates that gives you a way of doing probability theory that is abstract and doesn't rely on any particular model. And because it's string diagrams, this is all a formal language. This can be translated into code. So this is a translation to code of the string diagrams I was telling you about, to pseudocode, of course. But you can have the implementation in Haskell, and I have that on GitHub. And then leave the computer calculate what is the correct solution, right? So depending on the assumptions that you put on each one of the boxes, depending on the string diagram, depending on the code you put, the computer is going to give you an answer or not to the problem. So now you can move to discuss the assumptions that you want to make when you solve Newcomb's problem, instead of arguing about what is the correct solution without making this assumption explicit. So this is, I think, the advantage that it gives to have a formal language for probabilistic decision theory. And this is what I hope to have convinced you that it's something that is possible, and that we all actually have some tools and some good ideas on how that can be done. So I think that's all. Thank you very much.
Great. Yeah, thank you, Mario. That was a very interesting talk, and it definitely left us with a lot of things to think about. So now we are entering to question time,
Yes,
for our colloquium. And for those who have been with us before, there are two ways. You'll know that there are two ways to ask questions. One is you could raise your hand, and I'll call on you to unmute yourself, or you could type your question in the chat, and I'll ask on your behalf. So yeah. So while people are still thinking about their questions, so Mario, I'm wondering, I have a simple question. Like, I think you said at the beginning that Bayesian inversion does not exist in Markov categories, but only in partial Markov categories. Can you explain again why this fails in Markov categories?
It's not, my point is not that it doesn't exist in Markov categories. This works the same in Markov categories. You would have no problem. Again, it would be a definition up to almost sure equality and so on, but that's fine. The thing is, even if you can have this, you get this Bayesian inversion as a solution to an equation, but you don't have a way of writing this. If you give some generators, you don't have a way of writing that in terms of those generators. So if I give you the boxes P and F, there is no way with the constructors of a Markov category that you give me the box F dagger P.
Well, I see.
Right. So the claim is not that you cannot do that. It has this is something that exists in many Markov categories, but it just doesn't follow from the actions that you will have the not only the solution, but that you can write the solution down.
Can you show the solution again? For partial?
Right. In partial Markov categories, so the thing you can do, even if you cannot construct even if you assume the existence of the Bayesian inversion still, the thing you can do now is to say, well, I have some prior F, I observe through a channel G some Y, and that is going to be equal to this. So at least you have a way now of describing this Bayesian inversion that doesn't involve you putting a box with the Bayesian inversion. I don't know.
Yeah, that makes sense. That's very nice.
So it's a way of evaluating the Bayesian inversion as exact observations. Yeah, but the point is not that doesn't exist. It does exist on Markov categories in general. You could do Bayesian inversions nicely, and I think that's part of the point why Markov categories are so successful for probability theory. The point here is you can do a bit better if you have discrete partial Markov categories with the price of a bit more of algebraic structure. Yeah, thank you. That's important to clarify. I didn't want to mean that you cannot do that.
Okay, thanks. Yeah, that's helpful.
Yeah.
I wasn't sure if my memory had failed me. So are there other questions from the audience? if you have a question, you can raise your hand. There was a comment that your handwriting is beautiful, Mario.
Thank you.
Hey, I actually have another question. So you mentioned decision theory at the end of your
Right.
talk on the Newcomb's problem. Can you share a little bit how what you are adding, the kinds of things that you add to the syntax
Right.
to get something that you can apply you can do decision theory. I think that's very interesting.
Right. I went to this very, very quickly. The idea is you don't need to add anything new to the syntax. So if you see here the string diagram, I still are only using copy, compare, and discard.
Mm.
There is a particular technique that you can use to encode the decision problems. And this technique is, we do this on the first paper that is called evidential decision theory with partial Markov categories. And there, if you apply this technique to decision problems, the solution that you usually get is that aligned with something called evidential decision theory. So I was saying before, there are multiple schools. If you do the obvious thing in partial Markov categories, you get the solution of evidential decision theorists. You can also encode other solutions. It's just that that's the one that comes more naturally. So we center the first paper around that. But I think it's interesting because we are not asking anything new to the syntax. We are using just the syntax of probability with comparators. So the ability to have observations and copy and discard as we had before. And we even have an implementation. We write the decision problems in terms of that implementation. It's a Haskell implementation. It's on GitHub, and we can get the correct solution, at least according to the people that would agree with evidential decision theory. Yeah, I think it's an interesting topic, but it's a topic that is usually controversial, and I would not like to claim that there's a correct solution here. It's just we get one of these solutions.
Do you talk about risk in that decision theory, computing of risks and finding like
Right. So I'm doing this in a very let's say toy examples, and the more the decision problems from things like Monty Hall and things. These are
okay.
But I don't see why not. You would try to use some language that allows you. Well, I need to take some decision with some uncertainty. I want to maximize for something. I can always write this decision on a formal language and compute with it. So that will work for decision theory in terms of risk, right? I have some risk. I know what is the risk? I'm going to try to.
Because you get something that you can apply straight away to machine learning, for instance, where there's a lot of focus on risk, loss functions and risks.
I do believe the syntax works fine. Perhaps the implementation, it would not be the most efficient thing in the world, but I don't think the syntax works fine. And the fact that it also works in continuous observations, and there is also a paper on that by Stein and Staton. The fact that you can do all of this for continuous probability is very interesting because we didn't have a principal approach to these things before, right? So I think it's interesting that we have this principal approach, even if it's not necessarily the one you would like to end up using, right? You may want to implement it in any other way. But I do believe it applies, I think.
Thank you so much. Yeah, that was great. That's really exciting. We have two questions now. I think there's a question from Michael and there's a question from Valeria. So maybe Michael, you can unmute yourself.
Hello, very nice presentation, thank you. You mentioned that you have a Haskell code. How do you use this diagram in this Haskell code? So do you use like graph representation, or do you have some other clever technique to easily process this?
So I think it's going to fall on the second one. With the clever technique being that if you look at the string diagrams, they are hypergraphs, right? With the copy and discard nodes. So each one of the wires is going to represent one variable of do notation. Each one of the nodes is going to represent one statement of do notation. So there is a theorem that says that do notation in Haskell constructs the free primonoidal category Orson generators. So we can use that and then quotient by interchange of monoidal categories. But the idea at the end of the day is these string diagrams translate into code by putting one variable for every wire and one statement for every node. So there is a direct translation of the string diagram, and then you just encode it as a hypergraph, as variables and nodes. So there is actually a one-to-one correspondence. And in the second paper, we go to proving that code into notation is going to give you the free discrete partial Markov category on some generators. So it's the correct syntax for this thing. It is one-to-one correspondence with string diagrams. So you don't go into implementing the graphical parts. I'm not doing the user interface. I'm just encoding the string diagram as a hypergraph and then using it. Does that make sense?
Yes, it does. I just wondered because Haskell has also certain edge cases, like category Hask has these bottoms and so. And I understand you also need the fixed point, probably. Am I correct?
So you are fine with all of this because the thing we are doing, I mean, when we prove that this is correct, we prove it in an idealized notation, right? I'm not going to include bottom. I'm not going to include the usual semantics in DCPOs or anything like that. I'm going to just do an idealized version of the syntax, and that you can prove that is the free discrete partial Markov category. So you prove correctness for an idealized fragment if you want. It would be too difficult to prove it for the full Haskell, but that's fine because you don't want to use the full Haskell there. You're fine with not.
Oh, okay. So you basically assume that it's all total and all evaluates to some value and then is correct.
You assume that this is restricted to some idealized fragment of the notation, but it's good, I think, because that's the fragment that gives you this freeness result. So in some sense, I'm happy with that. But yeah, you don't have arbitrary Haskell code and you can translate that to string diagrams. Is that the question? No, you don't have that. But you are fine because the problems you want to describe are fine without them. Thank you. Does that make sense? That answer?
Thank you. That makes interesting topic because always when you have very nice mathematical idea, it's difficult to interface it with the real code afterwards, and sooner or later, every decision procedure will be used in the algo. Thank you very much.
Right. Thank you for the question. That's very interesting indeed.
Thank you, Mikhail and Mario. So Valeria, you can unmute yourself and ask your question.
Hi, Mario. It's a very pedestrian question. I get that the partial Markov category is about not this distribution is not adding to one. I hope that's correct. That they can be less than one. But then I wanted to understand better the discrete version, because from what I understood, it means that you are adding this compare function to it, and then the Frobenius stuff, right?
Right.
The question is, I mean, would the compare function make sense? Would the compare function the comparators made sense without the partiality? And I mean, why do I kind of want and also there is the Frobenius kind of conditions that are not very clear.
Right.
So kind of how can I just do the second bit but not the first bit, or vice versa? Can you go over it again, please?
Yeah. Thank you. That's a question that many questions here. So the first one is you were saying that for the partiality we need to go to such distributions. We at the compare, we don't need to change the semantics, right? I have done that very quickly and without mentioning. You're right. We don't need to change the semantics when we use the compare because our distribution does have a comparator already. So the function that takes two inputs checks if they are equal. If not, it can return 0 probability to everything, and that's fine. Then we go. So,
but that's not the business that you said that's problematic because that leads to a measure 0.
Right. That would be problematic in distributions. That is not problematic in sub-distributions. Right. And in the continuous case is where it becomes problematic. In the discrete case, it's completely fine to have that. In the continuous case, we will have things with measure 0. In the discrete case, if we have a set of cardinality n, then everything can have probability 1 divided n, so it's fine. Now, can we do some parts of the, you were saying perhaps we can leave the Frobenius actions and ask for the totality to be left? Well, I think the problem with the totality would be that the compare could be discarded. If we keep the discard and the totality, the compare could be discarded and it will be equal to discarding both inputs. So that's too strong for any semantics to satisfy. I don't know though if there are other fragments that could still be interesting to look at, and we have just gone too quickly over them. That's an interesting question. I don't know. But this is the one that seems to work very nicely. If you put if you would give a unit to the compare, you would get already to compact closed categories, to hypergraph categories. That seems too much for most of the examples that we have, so we don't do that. And then perhaps there are other fragments that are interesting. I don't know. That's an interesting question. Thank you. Does that answer?
Yeah, I just want one more kind of on that.
Yeah, please.
The Frobenius conditions, I mean, are they related to other notions of Frobenius that, I mean, they look like kind of making a monoid, a comonoid, right? Kind of.
Right. So this is a notion of Frobenius that is, some authors call it a partial Frobenius structure. So there is a paper by De Liberty, Subocinski, and others that looks at these partial Frobenius structures that are a Frobenius monoid, a Frobenius algebra, but without the unit. That is the thing that we are missing. And they seem to be interesting and to appear in categories with partiality. So partial functions as one of these, and sub-probability distributions as one of these. So they seem to be interesting on its own, right? I don't think they are Frobenius structures, or you can recover them as Frobenius structures in the usual way. But they seem still to be interesting to give the Frobenius equation.
Okay, that's great. Thank you so much.
Thank you so much for the question.
Thank you.
Thank you. Thank you, Mario. Thank you, Valeria. So here we are going to end the recording. Okay. So after this point, we are not going to post the recording online. As some of you remember at the start of the talk, we couldn't get our YouTube live stream to work, but we will be posting the recording on YouTube later on for those who want to catch the talk. And Mario, if I'm correct, you are going to you'll be okay with sharing your slides with us.
Yes.
Yes, and we will post your slides on the Topos Colloquium website. So, okay, so the recording's off. Does anyone else have other questions? So I see that Yanis, you have a question. I'll read it. I'll ask on your behalf.
What are some areas that aren't coming? Yeah, I just asked if Mario, you can find either put the authors, or if you can find the reference to the Liberty paper you mentioned on the partial Frobenius.
Yeah. So the authors is Ivan De Liberty, Chad Nestor, Fosco Lorejan, and Pavel Subocinski. And the title I won't remember now. I'm sorry.
I think there's a Robin posted a link to a paper. It's called Functorial Semantics for Partial Theories.
Semantics, yeah.
Is that the paper?
I think so.
2020 paper.
I think so. 2020 paper.
Yeah.
Could be. Yeah. Thank you, Robin.
Yeah. Thank you, Robin.
Yeah.
Okay. Thank you for that question, Yanis. Are there other questions for Mario? Okay. Well, let's thank Mario again. This was a very interesting talk and discussion. Thank you so much.